All right, so the next speaker will be Fernando. He's been a Google Summer of Code student last year and also this year. And it's now also, well, not the other way around.
Oh. Under the...
Perfect.
Okay.
So last year he wrote most of the structured. He wrote the structured output interface of structured output learning interface of Shogun, and this year he's doing what's called MKL, large margin nearest neighbor classifier. Or what's this thing called? Yeah. All right. So looking forward to your talk.
Okay. So thank you, Søren, for the presentation. So this talk, as we just said, is going to be about structured output learning, mainly about an extension of SVMs to do structured output learning. So the first slide is about me, so we can skip this. We have already talked about this. So a little bit outline of the talk. So at the beginning, I will introduce structured output learning in general and give some examples where it has been applied or where you can apply it, motivating examples of the method. Later, I will go in a particular method to do structured output learning with that is based on the SVMs, idea, support vector machines. I will describe some the parts of this method, and later I will make some examples how to use the structured output learning framework in Shogun. Okay, so the structured output learning setting that I'm going to be dealing with here is within supervised learning. Okay, so we have here data that is composed of pairs of inputs or observations and outputs or labels. So in the slides, I'm going to be denoting with X the observations and with Y the output or labels. And our objective is going to be to obtain a function that, given an observation, is going to map to a label. Okay, so given an X is going to produce a Y. And in order to estimate this function, we are going to use training data, label training data. So this is in general what is what all supervised learning is about. So what is special about structured output learning is, so normally in machine learning algorithms, the objects in the input space are normally from any kind of type. So you can have their images, strings, etc. And you normally are going to be dealing with them as vectors. So they are from the very beginning vectors, then you just go on. Otherwise, you can apply future structures or kernel functions. But traditionally, the objects in the output space are atomic, are singular. They are represented by numbers. So for example, in regression, its label is going to be a real number or a real vector. And classification is just a single identifier from a discrete set. But this is not the case in structured output learning. In structured output learning, the labels are complex. They are going to be composed of multiple variables, and not just the state of these variables is important, but also how do they relate to each other, the dependencies between the variables that the label is composed of. All right? So let's see some examples of structured output learning. So in natural language processing, it's an interesting problem, the extraction of parse trees. So here, the observations or the inputs are going to be languages, sentences taken from the natural language, such as that one on the bottom. And the output is going to be the parse tree that is going to explain the syntactic form of the sentence. So here we can see in the tree, it's not just important which are the values of each of the nodes, but also what are the children of each node and its root, so the dependencies between the variables. So another example or another application of structured output learning taken from the computer vision domain is segmentation. In particular, binary segmentation I am showing here. So here the inputs are going to be images, and the outputs is a segmented version of the image. So a segmented version of the image, in the case of binary segmentation, is going to be an image where each pixel is going to have one of two values. One value if it belongs to the foreground or a region that is of interest in the image, and another value that here is represented with black pixels if it's not in the foreground of the image. So here the labels can be each label is going to be composed of multiple variables that represent the pixels in the image. Okay? Now I'm going to talk about how the SVMs, the support vector machine, is extended to, or can be extended to be applied to structured output learning. So first approach that we can think of, the naive approach, would be to consider each label in the output space as a different class, and then apply multi-class classification accordingly, using, for instance, Kramer-Singer's formulation. This is in general not a good idea, since it gives rise to too many classes. So just to get an insight of it, so think of an structure output application where your labels are sequences, and each of them can just take, its node in the sequence can take one of two values, and they are, say, like of length 250. So this will give rise to the power of 250 different classes, which is a number that is comparable with the number of atoms in the universe. So you cannot aim at applying multi-class classification when you have such a number of classes. So we have to think of alternative approaches. One of them is, so we can map together observations and labels to a fixed dimensional space. So this has the nice property in that it becomes, again, a geometrical problem similar to the ones we are used to be dealing with SVMs. So the similar principles can be still applied. So this mapping of labels and observations together is what we normally call in structural output learning the joint future map. So, and it's important to note here that we have to take into account two different kind of interactions. So there are interactions between the variables of the observation and the variables of the label, but also interactions between the different variables of the labels. So here we see that there are links from the nodes that are blue, that those are the nodes that are in the label, and the nodes that are in red, that those are the nodes in the observation. So these links in here represent will be interactions between observation and the label, and also the links between the blue nodes are interactions between the parts of the label. And so the insight of just this gene future map is that we want to map in the output information that in the observation and in the labels comes from different dimensions. So we map them together. So another point to take into account is how we're going to make prediction. How we're going to, so given an observation, how is the structure output SVM, how is it going to find the label that corresponds to this observation? So this is going to be maximizing a linear score of the model that is an hyperplane, as in normally in SVMs, and the joint future mapping. Okay, so what we have to search is, in this space of labels, we have to search the one that maximizes that score. So how can we solve this problem? So again, a naive approach to do it will be to perform exhaustive enumeration. But as we said before, these spaces are going to be really large. So this is not feasible. Sorry. So so in order to solve this Rmax, what we are going to do normally is to exploit the structure of the output space. So for instance, if the labels are always sequences, take the form of sequences, then we can apply the Viterbi algorithm to solve this efficiently. If they are trees, as in the natural language processing example, then we can apply this other algorithm, the CYK algorithm, that is also efficient. But I think it's more interested in graphs in general. So if you don't put restrictions into the labels and they are represented as graphs, then there is no general efficient algorithm to solve this. So you can either use approximations or again find a subset of Y in which efficient inference is possible. Okay. And one last part, so far until now we have seen that the structure output SVM has the joint feature mapping. We have also seen a bit how does it perform prediction. And a third part of it is the loss. The loss is important not only to, so first of all it's important because once we make a prediction, we want to have a measure of if this prediction is good or not, to have some kind of measure of the accuracy or the error of our predictor. But also, it's interesting during the parameter estimation of the algorithm to have a notion of a loss. Okay? So let's take, for instance, a predictor that it outputs, so two different predictors, let's say, and they produce two different outputs. So one of them that will be completely different from the ground truth label, and another one that is pretty similar to it, but it is distinct just in a few elements. So if we use the traditional 0-1 loss that is used with SVMs, so both these predictions would be ranked equally. And this is not something that seems intuitively a good idea here, since one of the labels is really different from the ground truth, meanwhile the other is similar. So we have to use normally other kind of, not normally, we have to use other kind of losses in structured learning. So the Hamming loss, that is a loss that takes into account element-wise, which are the elements that are equal, is a loss that is typically used here. So now let's switch probably to the most interesting part of the talk, that is about, so how is it the structure output framework used in Shogun? So a simplified class hierarchy of how it's organized. So we have here the C machine class, that is a base class in Shogun where basically all the machines are inherited from. And here enters our structure output machine that is going to hold a reference to the model, to the structure model. So this model is important in structure output learning because so it is where we are going to fit our joint future vector mapping that we talked about before, the prediction oracle or the Rmax, and the structure loss. So in structure output learning, depending on the application or on the structure of the labels you're dealing with, these methods, these functions are different. So the joint feature mapping, if you are dealing with labels, is not the same as if you are dealing with trees or if you are dealing with graphs. So the idea is that this C structure model is going to be extended for the different applications you are going to be using it for. Okay? And following here, the hierarchy, so we have the linear structure output machine, so it's just a structure output machine where we fix that there is a weight vector. And later we have particular solvers, such as this one that implements a primal solution of the structure output SVM. Okay? So I'm going to talk about now, well, I'm going to show code for a couple of examples, and they are dealing with label sequence learning. So I just want to show how the model looks like, how the observations and the labels look like in this application. So in blue, we can see the nodes that the label is going to be composed of. So we have links between one element and the next one. And in red, there are observations. So there is one observation for each node in the label. Okay? So how can we solve a problem like that using Shogun? So first of all, we are going to set up our training data. So we create our labels. In this case, since we are dealing with sequences, so sequence labels. So we pass it the number of examples, and later we could give one by one each of the labels that will look something like this, right? So here is I'm just using a binary sequence example. So we have a label that will be 0, 0, 1, 1, for instance. So this will be the labels. You will just use a method like add label. You give a vector like this, and that's already inside. So the features. So we are going to be using matrix features because each of the labels is going to produce an observation that doesn't need to be a scalar. It can be a vector. So this is the idea. So for each of the label nodes in here, is going to produce an observation that is a vector. So for instance, the first label 0 produce this observation, 0, 1, 2. The second one, 0, produce this other observation, 1, 2, 1, etc. Later on, so how do we perform training? So first of all, we create our model, our structure model that I showed before in the hierarchy class. We associated it with the features and the labels. And the to-state is just saying that the labels we are dealing with are binary sequences. Then we make an instance of our solver. So in this case, this primal solver of the structure output SVM, and we associated it with the model. We train it, and then once it's trained, we can, for instance, see what is the weight vector or what are the slack variables, etc. So how can we do this in Python? So we first import a couple of modules from Shogun. So here, instead of giving the data by hand and using this other method, simulate data, that is going to simulate two-state data, and it's going to produce a model already with the training data inside. So we create the primal mosaic structure output SVM. Similar as before, we can train it, apply it, and later we can use this other one object to print the training accuracy. Okay. Now I would like to talk about a couple of extensions of the structure output framework, because the structure output framework in Shogun was designed taking into account that it could be easily extensible. And the extensions that one can do are twofold. So one can one can implement more parameter estimation or learning algorithms that I didn't really talk about the learning part during the talk. But these will be solvers, the typical solvers for the structure output for the support vector machine. So how to compute this the weight vector, or if you are dealing in the dual, how to compute the alphas. Okay, but more interesting, I think. So how to extend the framework so you can use your own models for the application that you want to that you're interested in. So. And for this, in this case, the Swig with the director classes are really useful. It's a feature that I really like, and I'm going to talk about it a little bit more. So far until now, the examples I have put are about label sequence learning. But let's say that you want to do segmentation, binary segmentation that we talked at the beginning. So the labels in this problem, they are not sequences. They take the form of grid graphs, where each of the nodes represents the pixel. Okay. So then you need another structure model. Okay. But say that in Shogun you have the parameter estimation algorithm that you want to use, a learning algorithm that you want to use. So then you can implement directly here your structure model and use already the methods for parameter estimation that are implemented in there. Okay. And apart from that, using Swig directors, you can do this from Python, which is very handy, I think. So for instance, for this example where we want to do a grid graph model, so we will do our class in Python that inherits from the director structure model. And you would implement your 3 functions that you need to implement for every structure model. That will be the joint future mapping, the structure loss, and the predictions oracle. Okay? And just doing that, you could be using solvers that are actually implemented in C++. So these solvers will be calling functions that you have implemented in Python. And this is where the magic of the director classes comes in. That is, I think, is something really nice. So this is another example. I'm using another solver, not the primal mosaic structure output support vector machine, but some methods based on stochastic subgradient descent. But is more or less is basically the same idea as before. I create my model, I give it the features and the labels, solve the problem, training, and now, for instance, I gave here in the apply some test features, so I get test accuracy. So I can see how it performs in data that has not been seen during training. All right, so that was mainly everything. So thank you for listening and questions and everything.
Any questions?
Yes, so I really like these director classes that you can extend your model in Python. And I would like to ask, so you have some experience doing this. Is it like reasonably fast to do this?
So I have experience, but from the user point of view. So I didn't implement, for instance, the director structure model. I had to change a couple of things in there, but I just use it like from the user point of view. I just did this thing. Yeah. I created my own grid graph model to solve problems. But for what I have seen in the code is basically to implement a class where every method is not implemented. You have to have your header and your implementation file, but in the implementation files, the methods are basically empty. And I remember that there were some Swig clauses, like preprocessor clauses that I didn't really understand. But I mean, I think, so my opinion is, so seeing one that is already implemented, it shouldn't be too difficult to make a new one. So I think that Soren has really...
We had very early, we had a MATLAB, we tried something similar with kernel, right? So there was something wrongly configured in Swig, and we had a single kernel element which was going through some loops in MATLAB, whatever, right? So I guess it's efficient if there's an overhead in the call, right? So it's efficient if you don't do many calls. But if you do like one kernel element at a time, there's not much computing. So then the overhead is relative to the computing is probably minor, right?
So
that's what I'm expecting.
The overhead of using the director classes with respect to using pure C++ code, or?
Yeah. So I guess if I assume there's going to be some overhead in going back to the other interface and then calling that code, right?
Yes.
So, and if you do this many times, like for a single kernel element, that's probably not good. If you do it, however, for the whole kernel matrix, that's probably okay. Yeah. That's what I'm expecting.
That makes sense. Yes.
So may I? So I have a question. So usually.
Just a comment to this. I think it was like factor 10 or so slower when we tried this.
So with respect to using pure C++, or?
No. I mean, his question was how much slower is it when you use the director instead of using it directly in C++? And I think I did some benchmark with some methods back then when Yevgeny implemented these directors.
Yeah, so
and things was like the 10 times slower. But of course, these it's like Gunnar said. If you call this method just once, and then you do lots of computation in the method, then slowdown is it's basically no slowdown. Yeah.
But
if your Python code just solves the linear system, which is done via calling some C function from Python, what happens then? Is it slower, or is it just the same call?
That's all the same.
Oh, that's really nice.
No, it's really only the problem really is only that Swig implements some kind of I have no idea what the correct term is, but in what it does is you have a function in C++ that then Swig wraps to Python, and the C function is when it's called from the native C code, it will check if there's a Python function for this class for this, like overloading this function, and then call the Python function. And this has a huge overhead. I mean, not too big, but yeah, but big enough. If you have like high-level calls, like for example, you implement a new SVM with train and apply, then it would be basically zero overhead, because train and apply, I mean, you just call it once instead of a kernel which you call millions of times.
And how about in the structured output framework, those functions, how often do they need to be called? I mentioned delta losses.
So that depends on the method you are using. So for instance, if you use an online method such as this one, then you are calling them once per iteration, which makes it better.
Did you? I have two questions.
Yeah.
So, did you think about different regularizers, particular for structured output learning, which we did? We had very specific parameter structures, and we wanted to have specific regularizers. Let's say we were learning piecewise linear functions. For instance, we wanted to have that these piecewise linear functions are smooth. So this is a special regularizer, right? So that would be maybe useful to have as an additional component. You have the model, you have the it's the solver, and maybe the regularizer could be one additional thing.
It will be really nice to have it that way, because so actually right now there is in this here in this HMSVM model. So I'm using the same regularizer, but with the C parameters of the SVM. I'm using different C parameters for different parts of the weight vector. So that right now is hard-coded in this model. So it would be better if that is independent of the model and can be specified in another part.
Right. Yes.
Yeah, exactly. So that will be really good. Yeah.
That was question one, and then we have quite a bit of structured output learning done in Compile. Like for gene finding, we did structured output learning, and there is inference part, right? I mean, the structure prediction part that is in Shogun already. So not sure you found that. It's not. It's somewhere.
There is a Viterbi algorithm implementation.
It's a semi Markov Viterbi algorithm. So it is heavily parameterized and so on, right? So I was wondering whether you had a chance to look into writing a class around this.
So I look at it, and I also asked Søren, but he told me that it should be easier, like to re-implement a Viterbi algorithm for my task than to try to understand that other one. So
I can explain that algorithm in detail to you, if you like. But it probably takes a few hours. But there's tons of time gone into that to optimize it and to make it suitable for the semi-Markov.
Okay.
I mean, weeks or months of computing of my time probably to improve and to speed up this, right? So maybe it's useful. I agree. So, but it's tricky, but it is there for a reason. So the complications are there for a reason.
But so the doubt that I had also respected to that is, so this Viterbi algorithm is thought to be in a semi-Markov model, but can it also be applied in a model that is not like that? So setting some parameters. So the semi-Markov model is like, it has also parameters for the duration that are you are just staying one state, right, or something like that.
So the semi-Markov has one additional parameter for how long your jump back can be at most, right? So and if you set it to 1, then it's a Markov model.
Okay, so that can be like set fixed and not introduced in the.
Yeah, I mean there might be a simpler implementation then, but but in principle you can can make a Markov model out of it. Yes. Yeah. And we have other structured prediction inference methods implemented, not in Shogun. I could give you that as well if you like.
I implemented 3 inference methods on general graphs, and I can give you this code, but it's in C, so you have to port it to fit into Shogun.
So what are the methods you implemented?
So it's exact inference. It's inference via Gibbs sampling and loopy belief propagation.
Okay.
So it's all.
Oh, that will be really useful. So, I mean, there is right now one ongoing project that is on structural output learning, and the aim is to do it for general structural output models, so graphs. And we have so that project is not aiming at implementing the inference solver, so at wrapping other code. So maybe your code could be the one that is wrapped inside there.
Hello. I'm currently working a bit on a general framework for doing sampling via MCMC. I just heard this word Gibbs sampling. So are there inference problems in those type of models that could be solved with like general purpose samplers?
Yeah, so the thing is like here, so when you are dealing with labels that are sequences, you have this algorithm, okay, the Viterbi algorithm. If you are dealing with labels that are trees, you have this other algorithm. If you are dealing with graphs that are in general, the problem that you have to solve for prediction is equivalent to inference in graphical models, in probabilistic graphical models. So then is when your problem appears that you are applying Gibbs sampling. But it is the same problem, the one that needs to be done in here. I believe. I think, okay.
You should also try kernel belief propagation then.
Kernel belief propagation, okay. So the method that I have tried for inference in graphs is a linear programming relaxation that you can use. So I use it from Python, so there is already a library in Python to do that directly, so it was really easy. And I have also tried GraphCut methods, but just because I find those algorithms fun. But I didn't try loopy belief propagation on these algorithms. Use sampling and so on. Okay.
All right, any more?
Thank you.